Okay, so the last thing we're going to learn about in this unit is how to calculate the acceleration due to gravity for a planet or a moon. Okay, so last semester we learned an equation for the force of gravity, and that is this equation right here, Fg equals mg. Okay, now it turns out that this equation is only approximately true, so Fg is only approximately equal to m times g. And the reason it's an approximation is because in reality, the acceleration due to gravity is not a constant. As we'll see in a moment, it actually depends on the distance you are from the center of that planet or the moon. Okay, so the grown-up equation for the force of gravity is the one we've been dealing with, and that's Newton's law of gravitation, and that's the g m1 m2 over r squared equation. Now, near the surface of a planet, you can calculate an approximate value for g using Newton's law of gravitation based only on the mass of the planet and the distance that the object is from the center of that planet. Okay, and so I'm going to roughly outline how to do that calculation, and then we're going to do some examples. Okay, so basically the way you approach this type of calculation is you hypothetically place a small object close to the surface of the planet. Now, you can make up a mass for the object if you want. It doesn't really matter because the mass of the object is going to cancel out, because what's going to happen is you're going to end up with the mass of your hypothetical object on both sides of the equation, and so it's going to cancel out. And then what you're going to do is you're going to apply Newton's law of gravitation to it along with Newton's second law. Okay, and so here's what we're going to look at in example 1. All right, so example 1 says, assume the Earth is spherical. A ball with a mass of 2 kilograms falls towards the Earth. It is about 6.37 times 10 to the 6 meters from the center of the Earth. The Earth has a mass of about 5.98 times 10 to the 24 kilograms. Using Newton's second law, calculate the acceleration of the ball. So what we're going to do is we're going to put the Earth, here's the Earth, and here is the ball, and I'm going to put the ball just above the surface of Earth. And I'm going to put the ball in free fall so that the only force acting on it is the force of gravity. Now notice I've given you the mass of the ball even though you don't need it, just because some people they enjoy having like concrete numbers. Okay, that 2 kilograms makes no difference. It'll cancel out like you'll see in just a second. Okay, now if this ball is in free fall, that means the only force acting on it is the force of gravity. And so let's apply Newton's second law to this problem. F net equals ma. Now, if we want to calculate the acceleration of the ball, that's the same thing as saying that we want to find a when the ball is in free fall. Okay, that's what acceleration due to gravity is. All right. On the left side of the equation, if we write down the sum of the forces, the ball is in free fall, and so we just have mg. Now I know the mass of the ball is 2, and the acceleration, because this is the acceleration due to gravity, I'm going to switch to calling this g, which is the symbol for acceleration due to gravity. And on the left side, I'm going to use Newton's law of gravitation. That's g m1 m2 divided by r squared. Okay, where r is the distance from the center of the Earth to the ball. So on the left side of the equation, I have g times the mass of the Earth times the 2 kilograms of the ball divided by the distance between the center of the Earth and the ball, which is given as about 6.37 times 10 to the 6 meters. That's squared. That's equal to 2 times g. Notice there's a 2 on both sides of the equation, and so the 2 cancels out. And so what I arrive at is that g is approximately equal to big G times the mass of the Earth. I don't know why I plugged in the radius already. I didn't plug in the mass of the Earth, but I plugged in the distance for some reason. So really this should be the mass of the Earth divided by r squared. And now here's really where I should plug in that value at the end of the problem. Okay, so 6.67 times 10 to the negative 11 times the mass of the Earth, which is 5.98, times 10 to the 24, divided by the distance between the Earth and the hypothetical ball. And again, it's hypothetical because if the mass of the ball cancels out, it doesn't really have to be a 2 kilogram ball. It could be any object I wanted. Okay, going back to the beginning of last semester, we learned that all objects in free fall, regardless of their mass, fall at the same acceleration due to gravity, and that's because mass cancels out on both sides of the equation. Okay, so anyway, so I need to divide by r squared, and I'm going to write the answer over here, but it should be very close to what we expect it to be. Okay, so I'm going to do 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 divided by 6.37 times 10 to the 6 squared. And the value I get is approximately equal to 9.83 meters per second squared, which is pretty close to the accepted value that we usually use of about 9.81. Of course, what you see is it depends on how far you are from the center of the Earth, and that depends on where on the Earth you're doing this problem. Also, keep in mind that we're assuming that the Earth is spherical, which it's not. And so we are making some assumptions here, which is why the answer is slightly off, but that's pretty close. Okay, and so that is how you calculate the acceleration due to gravity for a planet. So pause there if you need to look at that some more. Okay, so make sure you have this done in your notes, and then you're going to try example 1.5 on your own. Okay, so example 1.5 says, calculate the acceleration due to gravity for an object falling at the top of Mount Everest, which has an average height of 9 kilometers above the surface of Earth. It is about 6.37 times 10 to the 6 meters from the center of the Earth to its surface, and the Earth has a mass of about blah, blah, blah. Okay, so try to answer that question on your own. Pay close attention to the units, because you are going to have to do a unit conversion here, and see if you can do this calculation on your own. Okay, so in this problem, so let's say here's the Earth, let's say here's Mount Everest. I can't draw, so just pretend that's Mount Everest, and I have a hypothetical object in free fall near the top of Mount Everest. Now, if the radius of Earth is about 6.37 times 10 to the 6 meters, then I also need to add on, to find the distance between the center of the Earth and this object, I also need to add how far the object is above the surface, which is 9 kilometers. So in my equation, my value for r is going to be 6.37 times 10 to the 6 plus 9,000, because 9 kilometers needs to be converted to meters. Okay, so I'm going to type that into my calculator, 6.37 times 10 to the 6 plus 9,000, and I get 6.379 times 10 to the 6 meters. Okay, so now when I go to do my hypothetical calculation, I have F net equals ma. M is the mass of my hypothetical object. It doesn't matter what it is because it's going to cancel. So on the left side, I have G times the mass of the Earth times m, which is the mass of the hypothetical object. In the last example, I made it 2 kilograms. It makes no difference what it is because it cancels out. Okay, so here is the m on the right side, and then the acceleration to gravity, I'm going to start calling that g now. And of course, I need to divide by r squared over here. M cancels out, and so my new value for g is going to be about 6.67 times 10 to the negative 11 times the mass of the Earth divided by my new r squared, and so that would be 6.379 times 10 to the 6 squared. Okay, so this is the acceleration due to gravity on Mount Everest. So let's see what this gives us. 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 divided by 6.379 times 10 to the 6 squared. And I think I plugged that into the calculator wrong. Yes, I did. Okay, so I need to add parentheses on the bottom, and the value I get is about 9.08 meters per second squared. Okay, so that is the example for 1.5, or the answer for example 1.5. Okay, so hopefully you got that. And notice that the difference between this answer and for the last example, the last one was about 9.83, this one is 9.80. Okay, and so even though we're still on planet Earth, we've gone up to the top of Mount Everest. Relatively speaking, the acceleration due to gravity hasn't changed a lot, but it has changed enough to actually measure experimentally. Okay, so pause there if you need to look at that some more. And then we're going to see one more example. Okay, and again, I want you to try to do example 2 completely on your own. Here, an alien spaceship now teleports Mount Everest to the moon. Calculate the acceleration due to gravity for an object falling at the top of Mount Everest, which is now on the moon, which has an average height of 9 kilometers above the surface of the moon. Assume the moon has a mass of 7.3 times 10 to the 22 kilograms and a radius of about 1750 kilometers. Pay attention to the units there. State your answer to an appropriate number of significant figures. Okay, so pause it there and try to do example 2 on your own. Okay, so here is what the setup for this problem should look like. Without spending a lot of time talking through it, I will just kind of outline how it should look. Okay, so this is the mass of the moon. This is the mass of the object. Divide by r squared, where r is equal to 1700 kilometers plus 9 kilometers. That's 1759 kilometers. And then I need to multiply that by 1,000. Okay, so that's 1.759 times 10 to the 6 meters. If you just multiply that by 1,000, you get 1.759 million, which is 10 to the 6. The mass of the hypothetical object cancels, and so the answer you should have gotten is, let's see, 6.67 times 10 to the negative 11 times 7.3 times 10 to the 22, and then divide by 1.759 times 10 to the 6 squared. Okay, and so G on the moon, well, not quite on the moon, also on Mount Everest, which is teleported to the moon, is approximately equal to, let's see, 6.67 times 10 to the negative 11 times 7.3 times 10 to the 22 divided by 1.759 times 10 to the 6 squared. And once again, I have forgotten parentheses. All right, and I get about 1.57 meters per second squared, which is what you should have gotten for example 2. Okay, so we are now done with this unit. You should now be able to calculate acceleration due to gravity for a planet or a star or a moon. Okay, as always, please let me know if you have any questions, and I will see you guys in the next video.